So, did anyone work this out? This place we got stuck yesterday? What? It's not possible to write principal ideal 2 as a factor of 2? You can prove that? Oh, okay. Then that's contrary to what I can show. So let's see who is right.
The equation is somewhat wrong. Equation is
That's wrong. That's clearly wrong. That you showed last time that cannot be. How about this? Is this true? Okay, let's see that. I think this should be true. So we have to show inclusions two ways. Firstly, any element of this, which is, in fact, we can go back to yesterday's calculations and make use of it. We have an arbitrary element which is here. Of course, this is not quite what we would have. So let's see. Let's do it afresh actually. So an element here, which is 2 alpha plus 1 plus square root of minus 5 beta times 2 gamma plus 1 minus square root of minus 5 delta. That's a general element of this product. Of course, there are sums also, but each product, each term of the sum has this form. Okay, and if you multiply this out, this equals 4 alpha gamma plus 2 alpha delta 1 minus square root of minus 5 plus 2 beta gamma 1 plus square root of minus 5 plus this would be 6 beta delta, and this is in principal ideal 2, because each term, if you see, is a multiple of 2 and also belongs. So that's it. It's basically it's a 2 times some element of the ring. So that's whole ring is z square root of minus 5. Okay, so that's one way is clear. How about the other way? Like I said last time, it's enough to show that 2 belongs to this product. Does 2 belong to this product? Just multiply 1 plus square root of minus 5 So this sum of products is an element of this product ideal, because this is an element of the first ideal, this is an element of the second ideal, this is an element of first ideal, this is an element of the second ideal. And in the product ideal, the elements are finite sums of pairwise products. And this is 6, this is 4, the difference is 2. So therefore, the answer to this question is yes. So the proof that you worked out that it is not factorizable, there is a problem in that proof, I guess. Similarly, the principal ideal 3 factors as in a very similar way in this fashion. And you can see almost identically the connection or why this is happening. If you take a generic element of this product, which will be of the same kind except that instead of 2 we'll have 3, and you multiply this out, instead of 4 we'll have 9, 3, 3, and then 6 will remain. So all of this is multiple of 3. So this any element of this belongs to the principal ideal generated by 3, and conversely I can generate 3 in this. Basically the same thing. 3 into 3 minus this product is 3. So that also shows that the principal ideal of 3 also factors. So that's the factorization of 2 and 3. And if you recall, we had this equation. So let's see the right hand side of this equation. How about 1 plus square root of minus 5 and 1 minus square root of minus 5? 1 plus square root of minus 5, I will claim factors as it's again, look at the general element of this. What is that? Go back to the same picture. In the general element, there will be a 2 here and a 3 here. 1 plus square root of minus 5, 1 plus square root of minus 5. When you multiply them out, 2 times 3 would be 6. All other terms will be multiples of 1 plus square root of minus 5. And 6 is 1 plus square root of minus 5 times 1 minus square root of minus 5. So 6 is also multiple of 1 plus square root of minus. So this therefore is contained in this principal ideal. Conversely, is 1 plus square root of minus 5 contained in this? Yes? Why? 3 into?
1 plus square root of minus 5 minus 2 into 1.
Wait a minute. Now, we have to show an element of here times an element of here, and maybe some finite sums of such elements is equal to 1 plus square root of minus 5. So what is that equation you are saying?
2 into 1 plus square root of minus 5.
Okay, 1 plus square root of minus 5 equals 3 into minus 2 into 1 plus. Yes, so that's an element. This is an element here, and this is an element here. So this times this minus this times this. And 1 minus square root of minus 5 in a very similar way will factor as and now we can explain this seemingly different factorizations, because these, when you look at these in terms of principal ideals, they will factor as non-principal ideals, and I have not discussed it. In fact, we are still yet to decide on the definition of what a prime ideal is. But whatever that definition is, these are prime ideals as it turns out. I will not show that. I'll leave it for you to work out. And then 2 into 3 is this 2 ideals times these 2 ideals, and 1 plus square root of minus 5 into 1 minus square root of minus 5 is these ideals times these ideals. Both the products are the same. 2 comma 1 plus square root of minus 5. So this is a prime ideal, this is a prime ideal, this is a prime ideal, all these 4 are prime ideals. Okay. And now you see that you can write the reason why we get distinct this equality that 2 times 3 is 1 plus square root of 5 minus times 1 minus square root of minus 5 is that just a rearrangement of these prime ideals factorization. So that is an example of how this unique factorization property gets restored once we look at the ideals. So if you see this equation in the ring doesn't admit unique factorization. 2, 3, 1 plus square root of minus 5, 1 minus square root of minus 5, they are all irreducible elements in this ring. So you cannot be factored further, but there are two different ways of factorizing the number 6. So unique factorization property in this sense doesn't hold in the ring. Now when instead of looking at these as numbers, if you look at these as principal ideals, then we have unique factorization property again. As principal ideals, this is the principal ideal 6 is same as principal ideal 2 times principal ideal 3. Similarly, it is same as principal ideal 1 plus square root of minus 5 times 1 minus square root of minus 5. Now, moving to the ideal world allows us to further factor these principal ideals into prime ideals, which is what is happening here. Here and here. And more here is this. And now in terms of these principal ideals being factored as prime ideals, the unique factorization property is restored. Okay. So that was the original motivation why the ideals were defined. Like I said, Kumar was the mathematician who identified the problem and then tried to resolve it by defining ideal numbers, which were some hypothetical numbers, which helped resolve this or reinstate the unique factorization property. And then later on, Dedekind said, oh, these ideal numbers, instead of forcing them in, if we just look at ideals, just by changing the view, like I said earlier, that don't look at a number as a number itself, but look at a number or view the number as all multiples of that number. That, or in terms of now notation or terminology we have defined, look at the principal ideal corresponding to that number. And then this unique factorization property is brought in. About these ideal numbers of Kumar are, at least in this case, are these prime ideals. So their presence brings about the unique factorization. Fine. So this resolves this example, but we still haven't looked at the general case. But before we look at the general case, we still have to resolve that certain amount of confusion about the definition of what a prime ideal is. I gave two definitions last time. Did you think about this? The first one is quite natural. The second one seems strange, but let me suggest to you why this is also a possible definition of a prime ideal. We define ideals as, at least the principal ideals, as multiples of numbers. So in case of ring of integers, if you look at a principal ideal, all ideals there are principal, look at a prime number. Look at the principal ideal of that prime number, which are all multiples of that prime number. That ideal is a prime ideal in the second definition sense. Because if there is an ideal which contains this, so let's look at number 7. Look at all multiples of number 7. That's a principal ideal. if there is any ideal that contains all multiples of 7, what could that be? It has to be ideal, principal ideal 7 or principal ideal 1. Cannot be anything else because 7 is a prime. So that is this definition, the second one. That is, if you have a, there is no ideal between a prime ideal and the whole ring. So it does make sense, the second one also. So any comments about or thoughts about these two possible definitions? Are they equivalent? Sorry? Couldn't prove that equivalent. Actually, they are not equivalent in general. In fact, this factorization of ideals itself gets messy if the rings are not of certain kinds and somewhat nice kind. And similarly, this, or rather, I should say that if the rings are not of or not nicely behaved or not of a particular kind, then these two definitions become different. Even factorization of ideal itself is kind of not very nice. So we would see for prime ideal, there are such basic concepts that we would like a definition that is universal. It holds for all rings, and it can be done defined in a nice enough way. Since factorization of ideals is not very nice for certain rings, we will not use this factorization definition of prime ideals. So that brings us to the second definition. The second definition also becomes restrictive for certain rings, certain types of rings. We will see examples of this later, not now. For now, you just have to believe me. So we can't use the first definition. We won't want to use the second definition. So which definition do we use? We use a third definition. This is a new way of stating the definition. Ideal I is a prime ideal if for every AB in the ring, if the product AB is in the ideal, then either A is in the ideal or B is in the ideal. Now again, if you go back to the definition of or the setting of ring of integers, this is also very sensible definition. Look at a principal ideal generated by a prime number, and we are saying that if two numbers A, B, the product of two numbers A and B is in that principal ideal, then either A or B is in that principal ideal, which is equivalent to the fact that if a product is divisible by a prime number, then one of the two elements in the product must be divisible by a prime number. So that's one of the fundamental properties of prime numbers, and this definition captures that property. So hence this can also be used as a reasonably good definition of a prime ideal, and this is the one that we use across all the rings. Now it turns out that for certain types of rings, all the three definitions are equivalent. I will not show it, but I'll just kind of highlight that a bit. But the second definition that I had earlier given, that is still interesting enough, and it can be defined for all rings. So I will give it a different name. Not call those ideals prime ideals, would call them with a different name. Same definition, except the name I give to such ideals is now different. These are called maximal ideals. And there is, let me just show one connection that can be proven very easily over all rings. Which is that every maximal ideal is prime ideal. And this is good to know because this tells us that our definition of prime ideals is a more general one than the initial one that I gave. It encompasses more ideals. So why is every maximal ideal prime? Well, suppose I is maximal. And we want to show that I is prime. So consider A, B, this product in I. Okay. Now let us create two ideals. I1 being principal ideal of A plus I2 being principal ideal of B plus I. Both are ideals. Okay. Both contain the ideal I, and since I is maximal, what does it mean? It means that they are either equal to I or they are equal to R. If any of them, suppose if this is equal to I, what does this mean? That A is in I. And if that is the case, then we are already done. On the other hand, if A plus I equals R, then we have alpha A plus beta is 1. R contains 1, and this sum of ideal is R, so there would be alpha in the ring R, beta in the ideal I, such that alpha A plus beta is 1. Multiply this equation with B. Is B. Now this implies that B is in I. Because beta is in I, so B times beta is in I. AB is in I by assumption, so alpha AB is in I, therefore B is in I. That's a pretty straightforward proof showing that every maximal ideal must be prime. Now let's come to the situation where the definition that I gave. See, eventually I want, right now the target is to be able to express uniquely every ideal as a product of prime ideals. Okay, and I have been saying that this only holds for certain types of rings. And the types of rings where this holds are the ones where all, but at least these definitions coincide for the prime ideals. So let's define those settings. And in order to define those settings, if you recall, going back to our discussion on groups, we were able to express certain types of groups as a sum of copies of Zn plus some finite copy. What was the limitation, or what was the condition imposed on those groups? Finitely generated. See, if you go back to that result about groups, the structure of groups, the theorem stated that every finitely generated group can be expressed as sum of copies of Z plus a finite part of it, a finite group part of it, which further can be expressed as sum of Zp to the alphas. Right? So that structure theorem only was true for finitely generated groups, not for other kinds of groups. And I've been saying that it is this structure theorem for ring that I've been aiming for only holds for certain types of rings. And it turns out that finitely generated rings is in not rings only. Finite generation is an important component of that restriction. So for rings, how do we say that how do we connect this notion of finite generation with rings? With groups we had seen. What is the simplest finitely generated group? The one with just one generator. And then you all powers of that generator generate that group. So in case of the group being finite, it's a cyclic group. Otherwise, it's just a copy of Z. So what could be analogous notion of rings, a finitely generated rings? Let's say a ring with just one generator. Principal ideal? A principal ideal like, yes, that seems like a natural thing. The principal ideal, there is just one generator, right? All multiples of one element make the principal ideal. But then every ring has one generator only, because every ring is equal to, whatever ring that we are talking about is equal to principal ideal of 1. Okay. So we cannot limit our attention to saying that a ring is finitely generated or not. Well, in all rings in this sense are finitely generated. In fact, they are the simplest possible ones. So what we'll have to do, and this is a slight leap of imagination, that instead of looking at whether rings are finitely generated, we look at whether ideals are all finitely generated. A principal ideal is surely finitely generated. It is just a single, generated by a single element. Not all ideals are finitely are principal. We have seen that. In fact, if you look at this ideal, this is not principal, but it is sum of two principal ideals. In fact, this is just a shorthand to write this. So this ideal is also finitely generated. So in general, we can say an ideal we say is finitely generated if it can be written as a sum of finitely many principal ideals. And that's a very natural definition. And then we say a ring is a ring is called a Noetherian ring if all its ideals are finitely generated. Now, the name Noetherian is, as often the case, is named after the mathematician who first studied these kind of rings. The unique part of this name is that it's a woman, Emmy Noether. She was one of the earliest women mathematicians known, at least probably amongst the prominent mathematicians, she was probably the earliest woman mathematician. Okay. So, examples of Noetherian rings. We have seen examples of many rings. Let's go through them. Integers, surely Noetherian, right? All ideals are principal, so they are the extreme examples of Noetherian rings. How about these extensions? Z square root of D. 1 comma root D will generate everything. But what we need to show is that every ideal is finitely generated. Every element of this is of the form an integer plus an integer times square root of D. So if a ring, if an ideal has two generators of this kind, then by taking appropriate differences, we will get in that ideal an integer and one element being pure integer, another element being an integer times square root of D. Okay. And now individually on these you can apply the property of Z. So if there are two integers, pure integers in that ideal, then their GCD will also be in the ideal. So there will be a unique minimum integer in that ideal, and every integer in that ideal will be written as a multiple of this. Similarly for integers times square root of D. And then with just put all these arguments together, you will find that any ideal in this ring can have at most two generators. How about this? Zx. This will behave exactly the same way as this. See, the square root of D was So 1 and x are the two natural components, right? Yes. Even not even 1 and x. It's a, if you have, let's say, if you have an ideal, so elements of these are polynomials. If you have an ideal with two polynomials inside that ideal, the GCD of those polynomials will also be in that ideal. Correct? Of course, taking GCD, we have to be a little careful because we have coefficients are integers. So we have to ensure that there is an integral, all the coefficients are integers. But you can work this out. I'll leave this a small exercise to you, and you can work this out and find that this will also have maximum 2 generators, I believe. I'm not sure. It may also have, that is, every ideal here may also be principal. This will, you need to just check this out. So either 1 or 2, no more than 2 generators are needed for this. So that's very interesting. How about any other example of a ring that you know of? We are ruling out non-commutative rings. We are just focusing on commutative rings. In fact, lots of examples exist which have this property that these rings are Noetherian. So instead of giving more examples of this, let me give you an example of a non-Noetherian ring. And this example is also of quite a bit of interest because we'll develop on this subsequently. So let's define an interval, let's say -1 to 1. Okay, we are considering continuous mappings from the interval -1 to 1 to real numbers. Collect all continuous mappings in the set F. I will define arithmetic on this set and claim that under that arithmetic it forms a ring. What is the arithmetic? Very simple. Addition, take 2 mappings and define the sum of those 2 mappings as a new mapping. Will that be continuous? Yes, that will be continuous. What is the and this is also commutative and associative, this summation. How about the identity of this operation? The 0 map, which maps everything to 0, that's the identity of this operation. Then inverse. If you have map G, then -G is the inverse map, because G plus -G, this map, will map the entire interval to 0. So this forms a group under addition, commutative group under addition. Now you define multiplication of mapping also. So G1 times G2 is also a continuous map from the same interval. The identity of multiplication exists, which is the map which sends everything to all ones. This is commutative, it is associative, so it is, and then distributive property of multiplication holds for addition. All this follows all trivially, essentially. So that means F is a ring under addition and multiplication. Multiplication of maps. Okay. Now I claim that this ring is not Noetherian. And to prove that, what would I need to do? I would need to show an ideal in this ring, which is not finitely generated. Okay, let's do that. Consider ideal I of F defined as I contains all mappings G, G is in F, and G so I contains all the maps which are continuous on the interval -1 to 1, and G of X is 0 on certain interval around the number 0, around the origin. So essentially you have this is the origin, this is -1, this is +1, and your maps, any map which is of this kind, it is 0 in this part, and then it's continuous whichever way everywhere else, that's fine. There must be a non-trivial interval around origin on which this map must take the value 0. There will be lots of such maps, continuous. This is a continuous map. Is this an ideal? If G1 in I and G2 in I, this implies that G1 plus G2 is in I. Because if there is an interval around origin on which G1 vanishes, an interval around I on which around origin on which G2 vanishes, then intersection of those two intervals on that G1 plus G2 will vanish. So that's fine. Now G in I and G prime in F implies G prime in I. Because if there is an interval on which G is 0, then G times G prime is also 0 on that interval. It may be 0 on a larger interval, but certainly 0 on that interval. So I is an ideal, certainly. It could make the full interval trivial. That's also possible, yes. Okay, let's make it 1. Okay, good point. Okay, now I is an ideal of the ring F, and this ideal is not finitely generated. Why? Well, suppose I can write as G1 plus G2 plus Gk for some G1 to Gk in F. In fact, G1 to Gk not only would be in F, it would be, each one of them would be in I also. Has to be, by the very definition. Then look at there is an interval on which G1 vanishes. There is an interval on which G2 vanishes. There is an interval on each one of them vanish. Take the intersection of all those intervals and halve it, and cut it down by half or reduce it further, basically. Now define a continuous map which is 0 only on that reduced interval and non-zero everywhere else. There will exist such a map in F, and that map will be in I also. But this on this sum, the sum of these any mapping in this sum is going to be 0 on a larger interval around 0, whereas that new map that I have defined will be 0 only on a smaller interval. So it is not possible. So these are the rings which will cause problems to us if you are looking for that structure theorem. So we will not be able to prove any as nice a structure theorem about such rings. So for now, let's just focus on Noetherian rings. But it's not, unfortunately, sufficient that we are able to prove rather Noetherian rings are not sufficient for us to prove that structure theorem. We have to bring in some additional conditions. So we say that the ring R is a Dedekind domain if R is Noetherian. 2R is an integral domain. I have not defined what the integral domain is, which I will do. But unfortunately, even these two are not sufficient. We have to push in one more condition, which I don't even want to write down. So let's just keep in mind it's some small technical condition, which is almost always true. So it's not something very limiting or problematic. It's just that, if I want to write down that condition fully, I'll have to define two more things, which I don't want to do. But I do want to define what integral domains are. So we call a ring R an integral domain if whenever a product A times B is 0 in the ring, then either A is 0 or B is 0. This is a very obvious looking condition. Of course, this should be true. Certainly is true for integers or numbers in general. But this is not true for all rings. In fact, go back to the ring I just defined above. This one is not true for this. Why? The product, it vanishes everywhere. That's a 0. So again, in non-integral domains are very funny kind of, strange kind of rings, which are very interesting also, but not useful for, can be matrix also, very right. That's right. Yes. That's right. Absolutely. So while such rings are non-integral domains are interesting rings, and we will come across them later, but as far as numbers and their factorizations are concerned, we don't want them around. So that can't really handle factorization there. So that's why we bring in this condition also. And then there is an additional technical condition. All put together, the rings that satisfy them are called Dedekind domains. And then we have the theorem for Dedekind domains. Now we can prove the theorem about Dedekind domains, which I'll do next time.